as soon as I open my mouth, most of you realize, oh, he's not from around here. And I often find that when I speak, that a lot of people, well, where are you from? So let's just get that out of the way. There. I usually just say the United States, and people, they ask for more, and then I say Ohio, and they regret asking. Usually if you say I'm from New York or from Los Angeles, people will say, oh, I know where that is. But if you say anywhere from the vast interior of the United States, it usually doesn't click. I actually live in just outside a city called Springfield. Those of you who are fans of The Simpsons will recognize that location, except this is not the Springfield where the Simpsons live. We do not have a nuclear power plant. The reason that I live there is I followed my wife there when she made a job change. She taught at a university, Wittenberg University. It's spelled just like Wittenberg, a city that is not too far to the west of here. Although she's retired, we still go to the university often for events. We work out at the gym there. And one of the things that I've noticed that as I've gotten older is being among people who are considerably younger than I am creates the illusion, hey, I can hang with these kids. And then every so often I'll walk past the mirror and I'll say, who's that old guy that I'm seeing there? Oh, that's me. And so that brings me to thinking when I'm speaking to a crowd like this, where my first instinct is to say, oh, these are the people I'm used to working with, the young Jedi programmers that I was once. And I realize, but you're looking at me and you don't see Luke Skywalker, you see Obi-Wan Kenobi. So just in case I needed, I brought my lightsaber, which I may need. Now, so what I'm going to be talking about actually is, this is Code Dive. I will be getting into specific coding things, but part in my capacity as Obi-Wan, what I want to do is put it in perspective with the Force. And in this case, the Force that I'm going to be talking about is the underlying type system of the programming language. Something which I think people, we know about, but we don't really think consciously about. And I want to help bring that to the forefront in the discussion. But let me pave the way with a little bit of a story first. As you heard in my bio, I, over the years, wrote for publication. It started out as Embedded Systems Programming. It changed its name to Embedded Systems Design, and then it went out of print. It's now supported by a website called embedded.com. And like many commercial publications, they want to stay in touch with their readership. So they do these annual surveys. And one question that I find particularly interesting was this question. My current embedded project is programmed mostly in. Now, actually, when the magazine made its last print publication, the publisher asked me to write an unusual article. I usually write articles about coding, and I thought, wouldn't it be interesting to go back and look at several years of the answers to these questions and see if there were any interesting trends? And what I found was actually quite surprising. There it is. And now, just a little bit of insight here. This is a publication based largely in the US. They have franchises in other countries. There's embedded systems in the UK and embedded systems in India. But I think this sampling represents mostly people in the United States. It was about 1,500 developers. And I think there are a couple of interesting results that come from this graph. One is, notice where C is. C just blows everybody else away. It's far and away the most dominant language in embedded programming. C++ is a distant second. And the other thing to notice is the tilt of the trend lines, which that was the real surprise to me. I expected them to be in the opposite direction, that C would be going down. In fact, the same data indicated that C was declining during the late 90s and early 2000s, C++ was going up. And then around 2004, there was a bend in both trend lines, and they reversed direction. And so this is a kind of a curious situation, especially for someone like me. Although I am fluent in both languages, I am an advocate of using C++. And what this says is that, that basically a large part of the community is not getting the message. And so I wanted to talk about maybe why that is. And I think part of it has to do with the mindset. 40 or so years ago, a very prominent individual in the computing field, Edsger Dijkstra, made this statement that the tools we use have a profound and devious influence on our thinking habits. And I think that making the transition from a language like C to C++ does require a change in mindset. And although the point of this talk, by the way, is I am not going to be making very many broad comparisons about the effectiveness. What I really want to talk about is the thinking process that guides the choice of these languages and what it reveals about the underlying type system. And I think part of what's happening is that the C++ community is actually, with respect to the embedded community, is shooting itself in the foot by conveying the wrong message about the motivation for preferring one language over the other. And here's what I mean by that. It's that these days, sort of the preferred approach for teaching C++ is to use what I call the modern approach, the C++ as a new language approach, which is that you favor using the stream data structures as opposed to C's files. You prefer to use vectors, the vector class template instead of arrays, and you prefer to use strings instead of null-terminated character sequences. Now, this is in contrast to the way I learned C++. I learned C++ when none of those new features existed. There were no templates, there were no namespaces, no exceptions. In fact, the header file that I used on my first C++ compiler in order to be able to do I/O wasn't even called IOStream. It was called stream.h. It was a pre-standard version of that. So I learned C++ as the language grew to the new language that it is today. And I found that very comfortable, very comfortable. But what's happened now is that because the language has so many new and desirable high-level features, there is a tendency, and I've seen this happen in the industry over the years, is that a new wave rolls over the industry. For example, in the 1980s, artificial intelligence was a big topic in academia. I was actually on a university faculty back then, and it was almost as if you weren't doing AI, you weren't doing anything of merit. AI was going to solve every problem one could ever imagine being worth solving, and if it couldn't be done that way, it wasn't a problem worth solving. Well, that fever broke a few years later, and what were we thinking? And then a different fever attacked the industry. It was object-oriented programming. Everything was object-oriented. And what I mean is, if you weren't using inheritance and dynamic binding, you weren't solving the problem correctly. You say, but what if I don't need it? Doesn't matter. You need it. And that fever sort of broke. And what I'm afraid is that we're having a mild case of that fever again, where people are saying, if you're not solving your problem using vectors and maps and all these, you're not doing legitimate C++ programming. And the problem is that culture is so far removed from what the current embedded culture is. The people who are doing embedded development look at that and say, that's too big a gap. I don't see how to bridge that. So the irony here is that a key aspect that made C++ so viable in the market years ago is actually being discounted, in the sense that instead of telling people it's okay to learn gradually, to just incrementally add C++ features to your existing C code. It's like you got to throw it all out and do all these new things, or what you're doing isn't worth doing. And in fact, this was really amazing. Last week, I was at another conference, the Flight Software Workshop. The participants in this workshop were people who do software for spacecraft, the Mars landers, things like that. C is the language of choice, almost exclusively in that marketplace. But there's a sense, in fact, one manager told me, we tried hiring some C++ programmers, and they just couldn't fit into our, because here was this code base all written with arrays and pointers, and they wanted to use the STL components, and we just couldn't get them to mesh. We tell them, chill, back off. Just use some of these more primitive structures, and they couldn't make this work. And so, in fact, he told me we finally wound up adopting, just staying with C as a way of reining in C++ programmers who kept running amok. It's actually a management control. The lack of features became a desirable management control, which is kind of an irony. And so the idea that, this is the best way to do it, is possibly the enemy of just, isn't this a better way to do it? And so I'm not saying that teaching people to treat C++ as a high-level language is wrong. I'm just saying it's not a size that fits everybody. That for people who are doing commercial software on an existing code base, they're developing embedded software in C, the incremental approach is probably the right thing for them, because they can't just stop working, go off and study for a few months, and come back and completely redesign their software. They've got to work with what they've got and do it incrementally. And I have a sense that too many people are taking the attitude in the C++ community that that's not the right approach. Now, I want to be careful here. There will be, I'm sure, some of my colleagues in the C++ community will hear this and say, but I've never said that. And it's important to remember, in the famous words of Frank Luntz, it's not what you say, it's what people hear. And I've run into a lot of people who have heard that message as, if you're not using all these features of C++, you're somehow or another doing it wrong. And that is the problem. It's a communication problem. And so I'm going to be a big advocate for this idea of doing things incrementally. So, by the way, let's just follow this path, and then I'll come back to the thought I just had that I wanted to introduce. So here's a way to reason about this, is that certainly among communities of embedded developers like spaceflight engineers, they have very high standards for reliability. Things have to work. It's pretty hard to fix it once you've launched it. And now, there are ways to do uploads and stuff like that, but it's better if it works in the first place. And so what I'm going to suggest is that the selling point to this community is to tell them, but there are ways, the best way to do this is, if you're worried about bugs, is not let them in there in the first place. This is the sooner rather than later approach that I'm going to be espousing. And it's very difficult to do it in C, and let me just give you a very quick illustration. Memcopy, it's one of the workhorses of the C library. It's pretty hard to write a C application that doesn't use memcopy. Memcopy can copy two arrays, one to the other. Here, let's use my lightsaber. It'll copy IY into IX, and you can specify the amount to copy. And so not only will it do arrays, it'll copy arrays of integers, arrays of doubles, it'll copy arrays of structures, and you say, well, what's not to like? It'll do whatever I ask it to do. Well, as you well know, it'll also do all sorts of things you don't want it to do. It will copy an array of double into an array of int, and the result will be that now that array of int contains gibberish. Or it will copy too much. In this case, I have it copying an array of double into an array of integers, and I'm actually copying more bytes than will fit into that array. It'll wind up clobbering more data. And interesting, when I gave this example last week at the flight software workshop, there were people in the audience saying, yeah, my software is full of this stuff. So it's not like I'm making this up as a contrived problem. It's really out there. And this is a key point then, is what does this do to the programmer's mentality? What it does is it breeds a very unfortunate mindset, which is that the way you should approach programming is just get the code to the compile so you can get to the real work, which is debugging. Now you laugh, and I meant it to cause a chuckle, but I'm being serious about this. This really is a mindset that is held by many, many C programmers. And it echoes what Dijkstra said. It's that the tools you use influences the way you think about solving problems. Excuse me. So what's the alternative? And what I'm going to advocate is that you want to program in a style that turns potential runtime errors into compile time errors. And unfortunately, this is hard to do in C. It's much more viable in C++. Now, before I go any further, I want to say this is something we aspire to. It's a goal you target. You never expect to get there. You can still have plenty of logic errors in your code. And there are other sorts of analyses that you can do to defend against that. But this is, I would suggest, an approach which really gets you to cut down on the amount of errors that actually make it into your running program. Now, this style is grounded in some very basic properties of programming languages. And what I want to talk about is the type system. And again, I expect that many of you, all of you, you've used the terminology data type in normal conversation quite frequently. But what I find is that if I ask people to actually tell me what is a data type, they struggle with coming up with that definition. And what I want to do is really bring that to the forefront of your consciousness. I want to show you, I think this is a major discriminator between people who are just good at programming and people who are great at it. And so I think it's worth emphasizing this for a few minutes. Now, by the way, C and C++ use what we call static typing. It's not the only way to do it. There are languages like Python that are dynamically typed. I'm not talking about them. I don't want to get into a general comparison of the two. I simply want to observe that this is the nature of C and C++. We want to work with it the best we can. So one of the characteristics of a statically typed language is that you write declarations. The declaration says, here's an entity, a variable I want to use, and here are its attributes. And you give those attributes. Mostly it's the type. There is non-type information, like whether it's extern or static, for functions, whether it's inline or virtual. Not everything is type information, but type information is a major part of it. So as you well know, these are just declarations for objects. So the key point about static typing is that you tell the compiler, this is the type that it has, and that's it. It's set forever. It doesn't change during runtime. It doesn't matter what values you assign to it. It's static. It's fixed at compile time. So what are the benefits of static typing? Well, one of them is what we call operator overloading. Now, even C has operator overloading. It just doesn't have user-definable operator overloading. When you use the same operator with operands of different types, you're leaving it to the compiler to figure out exactly what you meant here. So this is an assignment of one character to another. You can expect the compiler to generate code that will move a byte. This is assigning an integer value to another int, you can expect the compiler to move something like a word. And here you have the plus operator being used for operands of integer type. One of them is a double. The actual code that's generated here is different for the two, but for the most part, we don't fuss about this. We trust the compiler. This makes our lives better. But let's get to the general question of what is a data type. Let's pause. So I want you to pause here. I will pause for you. Just think for a moment. If somebody asked you, what is a data type in a statically typed language? How would you answer that? Why don't you think about that for a sec, and now I'll tell you what my version of it is. It's that it's a bundle of compile time properties associated with an object. There are a bunch of predefined types, but you can invent your own. But it's really just a bunch of compile time properties. What exactly are those properties? They're things like size and alignment, which is really closely related to the more compelling, more interesting attribute, which is what is the set of valid values that an object of that type can have. And then this is profoundly important. It's what is the set of operations that are permitted for that type. So really, that's what I want to focus on. It's the set of valid values and the set of permitted operations. So in the case of int, for example, that the size and alignment on a typical 32-bit processor is 4. The range of values is that, and it's integers only. And then there are operations that can be performed. But just as important as the operations that can be performed are the operations that can't be performed. Think about what can't you do with an int? What is disallowed? Well, I'll give you a few examples. You can't dereference it. You can't use it as if it were a struct or a class and select a member of it. Ints don't have that. And you can't apply the parentheses as a postfix operator as if it were a function and say call it. These are all disallowed. Now, why are they disallowed? Who made this decision? Well, it's the language designer. In fact, if you look at the evolution of C, Dennis Ritchie took his best guess, and some of his initial guesses were wrong. The rules of early C allowed things that later dialects of C disallowed, and the basis was that people found that it exhibited behaviors that they found surprising and error-prone. And so they built that knowledge into the type system to say, well, if people keep screwing this up, maybe we should defend against it at compile time. In a sense, the compiler was turning runtime errors into compile time errors. So among the things that are also allowed are implicit conversions. And this is profoundly important here, the set of implicit conversions. Let me give you a really good example. I think this is one of the most confusing aspects of C and C++, is that if I asked you, now, think about this from the compiler writer's perspective. If this were the declaration not of x square bracket 10, but it just said int x, and I said, what do you think the compiler recorded about the type of x? You'd say, oh, it's an int. No question. It would record information in the compile time symbol table that x is an int. But what does the compiler record for that? Pardon? A pointer. Yes. Thank you very much for offering that. That is a very common response, and very interestingly, it's wrong. But thank you for playing. Here is actually the answer. It's that it really is an array of 10 elements of type int. That is what is recorded by the compiler. It is not a pointer in the sense that that is a pointer. These are fundamentally different things. So the question is, why is it that so many C and C++ programmers get tricked into thinking that the inherent nature of that array is that it's a pointer? And the answer is because you can do an assignment like that. You can take X, which is an array, and assign it to a pointer. But what's really happening is that there is an implicit conversion taking place. And that the colorful terminology we use is that we say that the array decays into a pointer. What's really happening is that there is an implicit array to pointer conversion, which takes that X and treats it as if it's the address of its 0th element, and that really is a pointer. But what's happening inside the compiler is this. It's very similar to this problem right here. You have a double and an int, and you know that you can add a double plus an int. And we say informally that it converts I to an int before it converts I to a double before it adds it to D. But the reality is it's not really converting I, it's creating a temporary object and initializing that with the value of I, where that temp is a double, and then it adds a double plus a double, and then throws away the temporary. That's why they call it a temporary. It doesn't last very long. And that's what's happening with the array and the pointer. But the difference is that with the array and the pointer, it happens so often that people get tricked into thinking that the array is a pointer. But it's this conversion that's taking place. And one of the differences between C and C++ is that C programmers can get away with the illusion that arrays are pointers and not get burned any worse than they're already getting burned by the language. But C++ programmers, the lack of awareness of these subtle issues in the type system can actually impede your use of the language, especially when you get to function overloading and when you get to template argument deduction, because these things really come to prominence then. Now, just to make the story a little bit more complicated, it's that notice that back on my earlier slide, I declared the array as a local variable in a function, and I said it really is an array. But when you declare an array as a parameter to a function, this is true in C and C++, it immediately transforms it into a pointer. That array right there, that is a pointer. These are all pointers. And so that it makes the excuse again for why so many programmers are confused about this, because there are contexts in which what looks like an array declaration actually does declare a pointer, but not when it's a global variable or a local variable or a member of a struct or class. So again, the C++ as a new language approach says, well, let's just avoid arrays and you won't have those problems. If you use vectors, you just treat them like they're first-class objects, and these things become non-issues. The problem is that if you're an embedded developer working on existing embedded projects, the code is peppered full of arrays. And it's very, very difficult to justify economically ripping all of that out and replacing it with vector objects. Those are the kinds of projects which tend to have a high failure rate. And so the transitional approach becomes necessary. So how do you make the case to people who are in this culture of, let me back up just a moment. What I want to emphasize is that there's a lot of recent work being done on cognitive science in this area called framing. A frame is a mental structure which really constrains the way you think about the world. And I think this idea that the real essence of software development is debugging can be labeled as a frame. And so if you are a C++ programmer and you were talking to somebody who has this mindset that the real work, the difficult work is debugging, and you say, look at these great features like classes and inheritance and virtual functions, aren't they wonderful? And you're saying this to somebody who thinks that debugging is a big chore, and they're sitting there and saying, how is this going to affect my debugging? It looks like it's going to make it worse. And in fact, they're probably right. Because that is, if your mindset is, I'm coding in C++ with the expectation that I'm going to have to debug this, then all those layers of abstraction, which in the source code may have made things hang together better, actually become impediments when you're single-step debugging through your code. You have to take a different mindset. So you're there extolling the virtues of all these other features, and the other person is just listening to you and saying, yes, but what's it going to do to my debugging? And they're not hearing all this other stuff. So you have to talk to people on the level that resonates with them. And so what I'm going to suggest is this. Oh, by the way, just an item which I had forgotten. I'm making the segue a little too soon, is that in the perspective that I was just painting about the type system, basically a C structure is a user-defined type which has fairly lax requirements on or constraints on behavior. And what a C++ class is it's basically the same thing, but it lets you specify a set of rigorous requirements on what the permitted operations are. And once again, excuse me, the idea is that data typing helps prevent accidents. And where I'm headed is I want you to learn, I want to emphasize the importance of understanding the type system and using that type information to turn potential runtime errors into compile time errors. Let me talk for a moment here about another difference in the type system, which is going to lead to a conclusion about programming style that reinforces the idea of turning runtime errors into compile time errors. C++ is actually stricter than C when it comes to pointer conversions. Here's an example like this. By the way, after many, many years of programming in C++, I just took it as a given that, of course, you can't assign a pointer to a double into a pointer to an int. And then I went back and I looked at the wording of the C standard, and even the C11 standard says that it is permitted to convert a pointer to a double into a pointer to an int. I was aghast, because most C compilers will not do that without complaining. But what you'll notice is it's a warning, it's not an error. They're just telling you, we as the compiler implementer, on our discretion, want to alert you that this is potentially hazardous. But officially, the rules of the language say it's okay. Now, I think it's good that it gives those warnings. C++ would make it an error. Now, of course, if you want to make the compiler be quiet and just let you do it, there's a way to do it. You write a cast. But putting a cast into something that transforms a pointer to one type into another, all it does is make the compiler shut up. It doesn't make the bug go away. If you actually go ahead and do this, what you will get is that it compiles and then exhibits what's called undefined behavior. Undefined behavior is the standard term for something bad is going to happen. And so it follows that you should use cast sparingly, very cautiously, because this takes your code in the wrong direction. It actually turns what were compile time warnings or errors into runtime bugs. It's exactly the wrong direction. So I just wanted to say that, yeah, you can make the compiler shut up, but you're actually going the wrong way. Avoiding casts can be hard in C. It's much easier in C++. And by the way, if you are going to use a cast in C++, you should use one of those. I didn't want to let that slip by, but I'm not going to elaborate very much. Now let's just look again at memcopy. If you look at the definition of the way memcopy behaves, it actually says that it does a character by character copy. I believe, in fact, it says it copies the blocks of memory as if they were unsigned characters, but I'm not going to get into that detail other than to mention it. But that's not the real declaration, because if that really were the way memcopy were declared, it would be too inconvenient. In particular, every time you use memcopy to copy arrays of anything but characters, you would have to put casts in here to quiet the warnings that or errors that you would likely get when you pass those things in. And any interface which continually makes you do casting like that is, again, it's taking you in the wrong direction. It's turning compile errors into potential runtime errors. So that's why memcopy really uses the pointer to void, pointer to constant void. And it avoids casting, but it sacrifices safety. In particular, the problem is that the pointer to void is actually a generic data pointer. Effectively, pointer to void is a pointer that always has a cast in front of it when you assign to and from it in C. In other words, it is very much akin to using a cast because you can do things like this. I can take a pointer to a gadget, a pointer to a widget. I can just take the pointer to gadget, assign it to a pointer to void, and then take the pointer to void and assign it to a widget. And now, without writing any casts at all, I have taken a pointer to one type and turned it into a pointer to another type. This is a dangerous thing to do. It's likely to result in a bad behavior at runtime, but you get no compile error. You've used void, in effect, to silence the compiler. It's the wrong direction to go. Now, C++ is a little more restrictive in that it lets you go from void into non-void. I'm sorry, I misspoke. It lets you go from pointer to non-void into pointer to void. That does not require a cast, but going back the other way does require a cast. So this won't compile in C++. But again, using the cast here is the wrong direction to go. It's still a dangerous thing to do. So once again, I'm giving you two pieces of advice here. Stay away from casts, stay away from pointer to void, because they effectively they take your program in the wrong direction. They take things that were compile errors or warnings, and they turn them into things that'll probably fail at runtime. Now, before I go on, I want to inject one other piece of advice, and then I'm going to take all this together and start applying it to some real code. Scott Myers, who was here last year at this conference, he is well known for having written a number of books, Effective C++, More Effective C++, Effective STL. But he may be less known for a particular article that he wrote, which I think it may have been his best piece of work. And if you go to Scott's website, I believe he has the article posted on his website, so you can just do a web search on Scott Myers' most important design guideline. And here's what he said, which is, make interfaces easy to use correctly and hard to use incorrectly. And I think that's a brilliant piece of advice. And I'm going to leverage that in the remainder of my talk here. I think it meshes very nicely with my advice, which is that you want to program in a style that turns potential runtime errors into compile time errors. And so memcopy, let's look at memcopy critically. It satisfies neither of those criteria. It's neither easy to use correctly, nor is it hard to use incorrectly. Once again, this example, as we saw before, it looks like that. It forces you to specify the size of what's being copied, and that's where it's very easy to make a mistake. And so what I think would be easier to use correctly would be something like this, where the compiler figures out the sizes that are involved in the copy. And this would be even better, is being able to simply assign one array to the other. Now, you can't do that natively in C, and there's no way to overload the assignment operators for arrays in C++. But what we want to look for is, so what's the best thing we can do to change things? And again, the perspective I'm bringing here is, I'm talking about embedded developers who have a large C code base and have a great deal of reluctance to overhaul their code, throwing in classes and inheritance hierarchies and things like that. They're very skittish about this. So you want to give them something that talks to them where they are, that resonates with them. And it actually, once you get into this mindset, I think you will find that it colors the way you look at C++ programming in general. So, once again, the real problem with memcopy is that it lets you do things like fill arrays with garbage or copy too far, copy past the end. Now, before I completely dispense with C, what I want to show you is it is in fact possible to write a completely type-safe array copy in C. And the trick is that you make the parameter type a pointer to an array of whatever element type. See, this is interesting. We are used to the notion in C that if you declare an array parameter, it's actually treated like it's a pointer. But one of the little known properties of C that is also a property of C++ is that a pointer to an array actually preserves the array dimension as part of the type. And so you can write a function like this, which says copy an array of 10 characters to an array of 10 characters. And if when you call it, you pass it something that doesn't fit that, at compile time, you will get an error. This is a way in C you could turn a potential runtime error into a compile time error. But the problem is that you have to do this for every type that you're interested in and every dimension that you're interested in. And it soon becomes an explosion of functions. Now you could say, but I could use macros and generate this kind of stuff. And maybe, but again, it has real usability issues, real problems with packaging. And so, but C++ gives you a pretty nice alternative approach. You can use a function template to solve this, where if you want to be able to have an array copy where you just specify the array that you're copying to, the array that you're copying from, and have it fully checked as to are they the same type, are the dimensions going to match? And that's a very easy thing to do in C++. So it turns these things that would have been runtime errors into compile time errors. And the key is understanding the type system, understanding the information that the compiler keeps around at compile time. And so in C++, when you write the template, and this is the part I want you to focus on, notice what the parameter type is. It's a reference to a function with a particular dimension that has an elements of a particular type. And one of the properties of references in C++, just like pointers to arrays in C, is that the array doesn't decay. It retains its arrayness. It doesn't become a pointer. And so it means then that the array dimension and the type can be deduced by the compiler. And so you can write a template which has type parameters t and a non-type parameter n, and you can simply say that the constraint is that the source and destination arrays have to have the same dimension and the same type. And you can give this to a C programmer, and I believe they will be quite comfortable with this. There's very little magic in this. When they say, and when I go to look at the generated code, if I have to debug it, it'll look very familiar. It'll look like what I would have gotten from memcopy. And so and then you can say, oh, and by the way, you won't have to debug it. But they'll discover that on their own. That's something that, because their mind operates in a frame of, I expect to have to debug this stuff. And then gradually, oh, but this doesn't need it. Eventually that frame changes. And it is possible to write things which turn runtime errors into compile time errors. So I want to emphasize, it's this insight into the type system of C and C++, that these things are pointers, but that is not. That is really a reference to an array. And this more than anything, these examples that I'm going to be giving you over the next half hour or so are really just to illustrate to you this mindset of really understanding the type system and using it during the construction of templates and overloaded functions. Oh, and by the way, and in modern C++, it's also these same rules apply in the use of the keyword auto, which does type deduction very similar to the way function arguments are deduced. Now, I believe in the example that I showed you where I wrote the for loop myself, you will find that most C++ compilers generate code which competes very effectively with memcopy. But if it turns out, for some reason, that on some compilers, memcopy is actually an intrinsic function. It calls upon machine instructions which do block moves, which are not necessarily ones that the compiler would select for optimization. And if that happens to be the case, you can always just make your implementation of array copy be a forwarded call to memcopy. And now, because this is an inline, it's going to be pretty hard to argue that's going to have the same performance as memcopy. So there are ways to adjust the implementation. Now, if you switch to memcopy, though, the reality is that this template is really creates the illusion that it will copy arrays of any type. It'll copy integers, it'll copy doubles, it'll even copy string class objects in C++. If you were to invoke this array copy on an array of strings, you might get a very disappointing result because it would bypass the string assignment operator and do a byte-by-byte copy, which would be a shallow copy. Well, once again, you can call upon the type system in C++ to help you with this. There is a mechanism called a static assert, which is the way you can, if there is a condition which can be evaluated by a constant expression, something that can be evaluated at compile time, and you can put that assertion in there to say, I want to prevent this array copy from being invoked on anything other than a plain old C type. If it gets invoked for something for which doing a byte-by-byte copy would actually give a different result than actually invoking the assignment operator, I want to know that at compile time. I don't want to wait and discover it at runtime. And so in modern C++, C++11, there are now these traits. You have to include the traits header, and you can say that if this is a trivially copy assignable type, then it's okay to do this. If this condition fails, it'll give you an error message that says it's an element type that has a non-trivial copy. I don't want to use this implementation on that. Again, it turns a potential runtime error into a compile time error. Now, the exact choice, we could have a long discussion on what is the right type attribute. There are so many of these type traits to choose from. It might be that you'd want to use isPod. In fact, I believe when I tested this, my C++ compiler, a particular vintage GNU compiler, didn't support this one yet. GNU, if it's added support, it must have been very recent. So I was able to test it with isPod, but I'm illustrating it with something that isn't supported on all compilers yet. Here's something, again, I'm just speculating on what the end user might consider desirable. The question is, if they can think it, can you implement it? What happens if I copy an array that is, in this case, the same size? That should be okay. If I copy an array that is larger to an array that is smaller, that should be an error because this won't fit into that. But if I copy a smaller array into a larger array, shouldn't that be okay? I mean, I'll only copy the smaller amount into the initial portion of that, and I'll leave the rest uncopied. It's not an error. One could argue about whether this is desirable or not, but I don't see anything erroneous about that behavior. If you want to allow it, augmenting the template is very simple. You add another non-type parameter which allows the two array sizes to be different. They have the same element type, but different dimensions. And then what you do is you put a test in here to make sure that you are copying from a smaller array to a larger array or from equal ones, but not into a bigger array to a smaller array. But notice something about this test. This test is really a runtime check. And it's checking things, M and N, which are actually things that are known at compile time. The compiler will deduce what those dimensions are as it's processing the template. It will know those values, so why wait until runtime to do that check? You might as well do that with a static assertion as well. Turn a potential runtime error into a compile time error. And I would submit that this is easy to use correctly and hard to use incorrectly. And it's a very good transitional machine to get your C++, your C programmers into C++ in a way that works for them. Now, the modern C++ also provides another class template, array. Array is essentially a wrapper around a built-in array that makes built-in C-like arrays look more like vectors. It makes it possible to use many of the standard library algorithms that use iterators and pass arguments of array types to them, and they will the algorithms will work effectively with the array class type. One of the nice things about the STL array class is that it actually lets you do assignment like that, which I believe is really the nicest interface, the one that's easiest to use correctly and hardest to use incorrectly. It does, however, have, one might argue, the drawback that it doesn't let you copy a smaller array into a larger array, something that would have been permitted by our more general array copy. But these are judgment calls about which of these things is more usable. The point is that you want to use the type system to craft something that is easy to use correctly and hard to use incorrectly. There are some other alternatives, like using the vector class. The problem is that, as I mentioned earlier, the vector class uses dynamic memory. There are a lot of embedded environments which simply don't allow the use of dynamic memory. And so using the array type, the array template, may be the best that you can do. Let's shift gears here to a slightly different topic. Now, later today, I'm going to be giving a talk on representing memory map devices as objects, in which I'll go into this subject in greater detail. But there are a few issues having to do with the sooner rather than later approach that I think are better illustrated here. So there's a tiny bit of overlap between this talk and what I will talk about later. When you do memory mapped I/O, basically the architecture says, I'm going to take a portion of the address space and I'm going to fake the instruction set into thinking that it's just ordinary memory. So I can use the same instructions that I would use for accessing real RAM or ROM or flash, and I'll be using them to talk to device controllers which are attached to the same memory address bus. So you can just treat those things as if they're memory. Now, what I have seen is very common practice. Actually, what I'm doing here is a little cleaner than common practice, is to declare this type def, which is a device register type, and it's really just an alias for a volatile 32-bit integer. And this is the thing that I really want to focus on, is that, in reality, it may be that there are 16-bit registers and 32-bit registers and 8-bit registers, but for my purposes, I'm just going to say, let's assume they're all just 32-bit ints, which is very common on, for example, the ARM architecture. And over the years, I've seen many of these C libraries that provide an interface to a hardware chipset or a single board computer, and they give you this big header file full of essentially macro definitions, which say that there's this hardware register called the TMOD register, and it resides at that address. So I'm simply going to take this integer value and cast it into a pointer to a device register, and now I'll be able to use TMOD as if it's a pointer to that memory mapped register. And just go on and do this for a whole bunch of registers. And I think this is very traditional, very common practice. And so once you have that header file, you can go ahead and write expressions that manipulate these registers. I'm sorry, this is actually a typo. That should have a star in front of it right there. But that wouldn't have compiled for various reasons. So that should have had a star. You can do things like store a character into a transmit buffer by saying dereference that pointer and store into it. Now, here's the problem, is that this is free software you can't afford. When I think about that heading, I'm reminded many, many years ago, there was a company called Cygnus Solutions. They were eventually merged or were bought out by Red Hat. And Cygnus, I believe, was the first company to be in the business of supporting companies in their use of open source, the GNU tool chain. And I saw them at many trade shows in the 1990s. And in those early years, they would wear T-shirts that say, "We make free software affordable." And I always thought that was a very clever slogan. Well, those header files that I just illustrated are fraught with danger, because if you write functions, like this is a put function which operates on a UART, and it requires that you pass it a status register and a transmit buffer register. And the problem is that both of those registers are the same type. They're both pointers to volatile unsigned 32-bit. And so what it means is that all of the registers have the same type, and they're basically indistinguishable from each other. So it's very easy to get the registers in the wrong order, or to take the status register from one UART and the buffer register from another, or to inadvertently pass a timer register to a UART function. And the compiler just won't say boo. It won't complain in the slightest, because everything is the same type. And as I say, this is really common practice, and it's a nightmare to debug this stuff, because the nature of the errors you get when you make these kinds of errors with hardware can be very spurious, very subtle. So a very simple thing you can do, and even this works just in C, is instead you take the registers and you cluster them together into a structure. And then you write functions like the timer enable or the timer get function, and what you pass is not the individual registers, but a pointer to a timer. And the beauty of this is that each one of these structure types is unique. If you pass the wrong type of device to a particular function, you get a compile complaint right away. Now, when you do this kind of a structure layout, there are issues about how can I be absolutely sure that these registers will line up the way I think they will line up, that there won't be spurious padding or alignment issues. And I will address those concerns in my talk later today. But I want to go on and say, so you can create a UART type and UART functions. And as I mentioned, the beauty of this is now this is easy to use correctly. You just pass the entire collection of registers, and it's hard to use incorrectly, because if you pass a timer to a UART function, a pointer to a timer is a different type than a pointer to a UART. You will get a compile complaint. Now, the problem with using a structure is that it leaves all the registers exposed to improper access, and this is where using a class becomes superior, because you can declare all the registers to be private and then have a set of public interface functions. And if you think back to what was the definition of a type, a data type is a specification of a set of values and a set of permitted operations. And by simply declaring these registers to be private, you have now restricted the set of operations. You've taken a whole bunch of what used to be invalid operations on registers, and you've simply made them inaccessible. So anyone who tries to poke directly at these registers in a way that they're not supposed to will provoke a compile error. But here is where it gets really interesting, is that many times when you deal with these kinds of registers, the vast majority of them are read and write registers. You can do both read and write accesses. But every so often, you bump into registers that are read-only registers, or that are write-only registers. And if you inadvertently write to a read-only register, what you get is very curious behavior, very hardware dependent. It could be something which creates the illusion that it's working sometimes and then fails mysteriously at other times. Sometimes you see a little puff of smoke coming off of the board. You just don't know what's going to happen. And similarly with write-only registers, if you try to read them, what you get is very unpredictable. So let me show you what you can do about that. Well, at first blush, you think, oh, that's easy to do. The read-only registers, declare them with the keyword const. You just simply make them const qualified data members, and that'll take care of that. But what do you do about this guy, which is write-only? There is no corresponding word in either C or C++ that says, give me something that is write-only. Well, what do you do about those things? And the answer is make a template. Turns out this is stunningly easy to do in C++, that you can create a general template for a write-only type and then declare UTXBuf to do that. Now, what do you think it's going to do? Think about it. Basically, it restricts so that the only permitted operations on that type are things which assign to it or initialize it by construction. And all other operations are disallowed. And I don't believe we have time to belabor all the details here, but I just want to show you, the functionality is pretty simple. You want to be able to declare a write-only object and have it initialized with a value. You should be allowed to declare them and have them initialized by default. You can assign to them, but if you try to do something where you read from it, that should provoke an error. That's what we want. And it turns out, implementing it, that's it. That's all it is. That it really just has three functions. It has a default constructor, which basically does nothing. It has a constructor that says initialize the write-only object with a value of the type that is inside the write-only object. Just uses a member initializer. And it has an operator equal, which lets you assign to it. This is a curious operator equal, though, an assignment operator, in that it does the unconventional thing of returning void. See, the conventional way that you write an operator equal in C++ is to return a reference to the thing that you just assigned to. But if you did that here, you would be allowing a read access. And so you have to do the unorthodox step of making it a void return. And that's basically it. What are these things? Well, these are just turning off the compiler-generated copy assignment and copy constructor, because they involve copying from something, and you don't want to allow those copies. And I'm using the modern C++ approach of using the equals deleted notation as the way I turn it off. But that's all there is. And it's easy to demonstrate that it works. I've been using this thing for years in my own work, and I've had yet to have any problem with it. I'm eager to find more people who are willing to try this stuff. I'm not getting a lot of feedback out there as to whether this works or not. So it would be nice for more people to try this sort of stuff. Now, let's revisit const, though, for a moment. Just a little while ago, I showed you that you could use const to declare read-only registers. It actually is a problem in C++. And it has to do with the subtlety of the semantics of const. Again, this is a good detailed case study of my point, which is to do this approach of turning runtime errors into compile time errors. The key insight is to understand the type system. Now, I don't expect people to memorize this stuff. I expect you to look it up. That's where I am, is that I just have an awareness that here be dragons. I want to make sure I get this to come out right. Let's go look at, see what the standard says about the behavior of this stuff, make sure my understanding is correct, and then test these constructs pretty thoroughly at compile time to make sure they do what you want it to do. Here's the subtlety, is that const in C++ really means that it is not modifiable once it has been constructed. And since you can't modify it after it's been constructed, it means your only opportunity to give it a value is at the moment of construction. And so the interesting behavior is that if you declare members of a class to be const in C++, it means those objects, those members, have to be filled in when the construction of that object occurs. So if you put a const in there, and you don't write a constructor for the class, you'll actually get errors that say you need at least one constructor that with a member initializer that will initialize those members. Or in modern C++, you can use the new the initializer in the member declaration Here's what I mean by this, is that if you put the keyword const there, you either have to write a member initializer in a constructor that will initialize that thing, or you can put an explicit, what's called an equal or brace initializer in the declaration of a member, and that says every constructor for this class will initialize this member when it runs. And in the case of a memory map device, this is not the behavior that you want. You don't want physical writes happening to those memory locations. So it turns out that the semantics of const are actually a mismatch for this particular use. So what do? Well, if C++ doesn't have it built in, you invent it. You make a read-only template to go with your write-only template. And you declare these things this way. And basically what a read-only object is, it's like const, except it doesn't have mandated initialization. It lets you fetch what's there, but it doesn't require that you put something in there to be fetched. And the implementation, the functionality that you want, I should say, is to be able to do this, to declare read-only only objects and to do a read like that. And this, in all the years I've been programming in C++, this is the only time I ever implemented a unary operator ampersand, the address of operator. The address of operator is a very curious function in that if you don't write it for a class, the compiler generates one and it does exactly what you think it does. But it can be overloaded, but most of the time you think, what would you ever want to do with the address of operator other than return its address? And it turns out I do want to return its address, but I don't want to return it as a pointer to a read-only object. I want to return it as a pointer to const, because that makes it usable conveniently in the rest of the language. And so that's the implementation. Again, you will have the slides. You'll be able to look at this lecture later and pore over the details. I actually, if you go out to embedded.com and look at the archive of my articles, I did go into considerable detail on how this got to be the way it is. But basically, it just has three functions again. One that is a default constructor that does nothing. One that is a conversion operator that is used to convert a read-only T into the T object that's inside of it. And there's the address of operator. It certainly has an interesting looking function declaration, but it's really not all that complicated. And the beauty of this is, again, it's lightweight. It does what it's advertised. You can go and plug it into existing applications without any architectural changes. It just turns a category of what would have been runtime errors into compile time errors. So, costs nothing in coder data space, costs nothing at runtime. So, here's basically the recap, is that what I've been encouraging you to do is program in a style that turns potential runtime errors into compile time errors. The reason that I think this is an easy thing to sell is that compile time checks generate no code. You can't see any trace of it in the executable. It's nothing to debug. They use no runtime, therefore, and this is very nice, whereas you can ship a program that fails a runtime check, it's pretty difficult to ship a program that fails a compile time check. Most customers are disinclined to accept things that don't compile. Scott Myers advises, and I echo, I think that this is really a very good principle to adopt. Make interfaces easy to use correctly, hard to use incorrectly. And the key is to use parameter and return types, to understand the type system, so that what you're doing is you're taking the operations that you're doing and you simply restrict them as narrowly as you can to the types for which they are really usable. Again, avoid casts and pointer to void because they take you in the wrong direction. And that's all I have to say. Thank you. And I think we have a little time for Q&A.
We've got about just under 15 minutes for a quick Q&A. So,
Okay.
Ladies and gentlemen, why don't you raise your hand if you'd like to ask a question, and these good people here will deliver you a microphone. I will point at people who will be asking questions. Just make sure that you are asking one to the microphone so that everybody can hear them, okay? You over there, please. The first person over there.
Okay, so you mentioned a safe alternative to a memcopy as a gateway to convince old embedded programmers or traditional C programmers to start using C++. Haven't you seen a situation where this leads to code bloat, and because of people using the multiple template instances, the size goes up, the performance goes down, and ultimately this results in a C++ that doesn't work situation?
Well, so the question is, have I seen instances where the use of of my array copies as an alternative to memcopy is causing code bloat? And what I first want to say is that the memcopy example was really, I wasn't trying to say, everybody go out there and do this. The real message is that you should look at the audience, look at what their concerns are. And I suspect that for many people in the embedded community, what they are concerned about is getting the bugs out of their code. And so you see what they are doing and say to yourself, is there available type information that can help me turn what they are doing into something that would fail to compile rather than make it through the build process and have to be debugged? And it may not be memcopy. It could be some different operations. But for my own testing, in the case specifically of memcopy, what my first version showed was doing a fairly traditional C loop for each element in the array and do an assignment. And I believe with most modern compilers, that will be optimized into something that is every bit as good as memcopy. But on what I showed shortly thereafter was, but if that turns out not to be true, you can simply make your implementation of array copy an inline function which calls memcopy, in which case the wrapping around that call to memcopy vanishes, and what you're left with is a call to memcopy. It's the same code as it was before. And my experience is that it's neither smaller nor large, it's just the same as those calls to memcopy. There is no bloat as a consequence.
Okay, I thought I saw the hand over there. Over there, please.
Hi, hello.
Why don't you just ask the question
Yes, you go ahead and ask it and I will repeat it.
You show some interesting example of how to meet problems while dealing with IOs and having to switch data between, for example, timer or SPI when handling users, for example. But you omit the problem when having several users in one project, switching user between each other. For example, putting data into one user while having to put it into another. Is there some interesting way, for example, having a special flag in the structure that you showed to have a certain of putting right data into correct user?
As I understand the question is, I gave an oversimplified example of an environment which only had one port,
Yes,
right?
but you show several users where
Yes.
problems could be, for example, putting timer data into a user because those are the register of the same type.
Right.
And you didn't say anything about switching user between each other, because if you have the same structure for each user I/O, then you could, for example, mismatch one user with another.
One user with another. Well, actually, this afternoon, I am going to be continuing this example, and I am going to elaborate that example by saying what happens if you have more than one. And so I think it would be better if you asked that question again at that session, having seen my more elaborate example of that, because I'm going to try to address some of those pragmatics. But I may even then not quite get to your question. At the end of the day, I'll be glad to talk to you at that time.
Over there, hugging the microphone already, please.
Yeah, can you hear me? Okay. Here I am.
Oh, there you are, okay.
I will
Yeah,
take
if you speak a little louder, I'll be able to hear you.
I will stick again to the copy array example because it's a representative for me for switching from C to C++. But my observation is that the actual issue...
Yeah, speak a little louder, please.
Yeah, okay. So the actual issue of the copying, as of the array copy example, is not the point-to-point copying of arrays, but the pointer arithmetic that is always sticked in the C code. So, for example, if you want to combine two arrays in the catenate reason or copy something from the, for example, fourth element of it, and I don't see how we can address that in C++.
I think I understand your question as, see, I was showing a very simple example where you actually had the original array declaration was visible. So you could write a template that would be able to see both the array address and its dimension. But if that array is being passed through layers of function calls, in C, they will be passed as pointers. And so in that case, you no longer have the dimension information. You may also have the situation where people are using things that are the equivalent of like stir cat, where you're appending arrays, and that gets more complicated. And yes, my simple example did not get to that level of detail. What sort of things can you do? Well, again, you look at the set of operations that you want to perform and you ask yourself, is there a way that I can take these operations and write, for example, a rudimentary, maybe it would be that I would write a rudimentary class that pairs a pointer and a dimension and pass those things. See if I can do that in a lightweight, type-safe fashion, which cuts down on the errors without incurring performance penalties. I confess, I have not followed that one all the way through, and it may be that at that point the right thing to do is transition to using something like the array class template that's in modern C++. But yeah, so I did not mean to dramatically oversimplify. I think it's that you just have to get into the mindset of looking at where is type information being lost? Is there a way that I can bundle it to preserve it and make that part of the interface? It may not, in a particular application, it may not be feasible, so you look somewhere else. But I think you will find that there will be those opportunities in various places in your code. I think you just have to try it.
One more question, anybody at the back?
Oh, there's one there on the right.
Very dramatic, I like that.
Yes. The problem is you're right by the light, and so you're hidden by the glare.
Hello. I wanted to ask you for your opinion, what is the safest language maybe, in terms of type checking?
What is the safest?
Safest language.
The safest language. Oh,
yeah.
That's
like in general, only for your opinion.
Well, it's not C++.
That's the question.
Yeah. Last week when I was at that flight software workshop, there were people who were working with Ada, small community people, and actually a variant of that, or a subset now called Spark, which comes with tools for doing all kinds of correctness proofs. And one of the attendees there had just written a book on Spark, and he gave me the copy, but it was only last week, and I haven't had a chance to read it yet. But I would certainly look into that if you were really interested in, extremely reliable, provable software. That's an area which I think is being actively pursued. But yeah, I'm sure I've missed something, and that's the nice thing I like about coming to these conferences, is somebody will come up and say, do you know about this? And I'll say, no, I've never heard of it before, tell me about it. And it gives me something to go investigate. So I can't really say much more than that. I'd say, look at Ada, look at Spark. You may find some interesting
honestly,
things
I was
there.
thinking about maybe Haskell or Coq. Do you know that?
I honestly don't know.
Okay.
And one of the things that I've learned as I've gotten older is that I no longer feel bad about not knowing everything.
I think we're going to wrap up
Okay.
on this happy note. Ladies and gentlemen, Dan Sachs.
Thank you.